Section 2.2 deals with infinite limits and limits at infinity. We're going to start by looking at infinite limits, and then we'll look at limits at infinity. Now, infinite limits, what that means is that when you're trying to find the limit as x approaches some number, you end up with the answer of either infinity or negative infinity. So those are what we call infinite limits. And infinite limits kind of describe vertical asymptotes. So let's look at the relationship between infinite limits and vertical asymptotes. What we say is that a function f has a vertical asymptote at the line x equal a if we can show one of these things. Either that the limit as x approaches a from the right of f of x is equal to positive or negative infinity, or the limit as x approaches a from the left of f of x is equal to positive or negative infinity. Now, please note, when we say that the limit as x approaches a number is equal to either positive or negative infinity, it does not mean that our limit exists. Actually, our limit still does not exist. We write positive or negative infinity to explain the behavior of the graph of the function at that value. So, for example, in section 2.1, like number 21, when we ended up with this rational function and we had 2 over 0, we said, okay, well, our limit doesn't exist. We won't do that anymore. When we have a rational functions can have vertical asymptotes. We would actually figure out, well, is this going to positive or negative infinity, and write that as our answer. Now, it just happens that in this case, the limit as x approaches 1 from the right of 1 plus x over 1 minus x is actually equal to negative infinity, and we'll figure out how to figure that out in a little bit. But there's a difference now in section 2.2. We no longer write does not exist when we have a rational function that we're trying to find the limit as x approaches a number. When we have a rational function like we do here, we are going to figure out, well, am I approaching positive or negative infinity? All right, so how do we do that? How do we figure out if we're going to positive or negative infinity? Well, there's a lot of different ways to do it. We're going to look at making kind of a table of values for the first one, and then we'll look at a shortcut way, and then we'll figure out how to do it just by looking at the graph. So let's begin with example 1. It says, given the graph of f of x equals 1 over x, we want to find the limit as x approaches 0 from the left, and then the limit as x approaches 0 from the right. Okay, let's pretend that we did not have this graph. So this graph, let's say it doesn't exist for us. How would we figure out what the limit as x approaches 0 from the left is of this function? Well, if we were approaching 0 from the left and we were to make a table of values, we would want numbers that are close to 0, very close to 0, and to the left of 0. So we might say, okay, well, let's try putting in negative 0.1. Let's try putting in negative 0.001. And then let's try putting in negative 0.00001. These are all numbers that are pretty close to 0, and they are to the left of 0. And on a graphing calculator, we're going to use a table to find this information. So I'm going to hit y equals, and then I'm going to plug in our function of 1 over x. And then I'm going to hit second and table set because I want to set up a table to find this quickly. And I just need to make sure that I change that independent variable. So I'm scrolling down to independent variable, and instead of auto, I'm going to scroll over to ask and hit enter. So then I hit second and graph for the table. And now what I'm going to do is, this is just a quick way for us to plug in all this information. And we're going to be doing this often using the graphing calculator. So I'm going to plug in the x value of negative 0.1, so negative 0.1, and hit enter. I get negative 10. Let's try negative 0.001. I get negative 1,000. And I'm going to also try negative 0.00001, and I get negative 1e to the 5th, which I'll explain what that is in a second. Here's negative 1,000. So negative 1e5 means you're going to take negative 1 and then add 5 zeros. So it's negative 100,000. So if we look at this, as we get closer and closer and closer to 0 from the left, it looks like our numbers are getting smaller and smaller and smaller, right? They are approaching negative infinity. So the limit as x approaches 0 from the left of the function 1 over x is equal to negative infinity. Now please note, again, my limit does not exist, right? It really does not exist. I'm just describing the behavior of the graph. And the behavior of the graph is that it's going down towards negative infinity. If we look at the graph itself, which we have over here, notice, again, here's x equals 0. If I'm coming in from the left, well, it looks like my graph is going down towards negative infinity. So looking at the graph, we can tell that the limit as x approaches 0 from the left is equal to negative infinity. One last way of finding this answer is the following. So I want you to pick a number that is to the left of 0, but really tiny. So in my case, I'm going to choose the number negative 0.001. So if I want to choose the number negative 0.001, I would pick 1 over, because here's my function, negative 0.001. Well, 1 is a positive number, and negative 0.001 is a negative tiny number. Now, if you take a positive number and you divide it by something that's negative, it becomes negative. And if you take any number and you divide it by something that's tiny, it's either going to go up towards positive infinity or negative infinity. In this case, because it's a positive over a negative, this is going to go towards negative infinity. So again, there's 3 different ways of looking at finding the answer that it's going to negative infinity. Most of the time, I think we should rely on the graph to find that out. But if you don't want to rely on the graph, any of those other options would work. So let's look at what is the limit as x approaches 0 from the right of f of x. If we were to just do this portion, I want a number that's to the right of 0, but pretty small. So I'm going to say 1 over, and then 0.0001. Well, the number 1 is a positive number, and this number 0.0001 is a positive tiny number. Now, a positive over a positive remains positive, and anytime you divide a number by something that's tiny, you go to either positive or negative infinity, in this case positive infinity. So the limit as x approaches 0 from the right of the function is equal to positive infinity. Again, if you look here, you can see it on the graph. We're going off towards positive infinity. Let's go back to that problem in section 2.1. I said that the answer here is negative infinity. Why is the answer negative infinity? Well, so I'm looking at the limit as x approaches 1 from the right of 1 plus x over 1 minus x. So I'm going to go ahead and plug in the number 1 into the numerator. I get 1 plus 1. And in the denominator, because the denominator is the one that gives me problems, the denominator is the one that ends up being 0, and I can't have 0 in my denominator. That's where I'm going to plug a number to the right of 1, but really close to 1. So a number to the right of 1, but close to 1 would be like 1.0001. If I add my numerator, I get 2. My denominator, and we can use a calculator to figure this out. If I take 1 and I subtract it from 1.0001, I end up with negative, and again that means just 4 decimal places. So this is going to be a negative tiny number. So negative 0.0001. So again, you have a positive number over a negative tiny number. And anytime you have something positive over negative, it's going to negative. And again, remember that either is going to be positive or negative infinity. So we end up with negative infinity. So the limit as x approaches 1 from the right of 1 plus x over 1 minus x. When we're in section 2.2 and from here on out, we don't write does not exist anymore. We determine where it's going, and it's going to negative infinity. The limit still does not exist, but we describe the behavior of the graph at that point. Let's continue on in section 2.2. So we know that we said that if we can show that the limit from the right of a is equal to positive or negative infinity, or the limit from the left of a is equal to positive or negative infinity, then we have a vertical asymptote at that number. So as long as we can show that the limit from the left or the limit from the right is going to positive or negative infinity, we can figure out that we have a vertical asymptote at x equals some number. So how do you find out what the vertical asymptote of a rational function is? So given a rational function, h of x, which is equal to f of x over g of x, your vertical asymptotes are always going to be located at any value x equals c, where the numerator doesn't equal 0, but the denominator does equal 0. So how do you find a vertical asymptote? What are we going to do to find vertical asymptotes? Well, there's 3 steps. The first thing we want to do is try to factor and reduce our given rational function, if possible. We're going to try to factor and reduce. After we factor and reduce, we're going to set the denominator equal to 0 and solve for x. And number 3, our final step is we will have a vertical asymptote, and I'm going to abbreviate vertical asymptote, V period A period. We will have a vertical asymptote at x equals any real numbers, any real number we got from step 2. Any real number from step 2. All right, so first factor and reduce. Then set the denominator equal to 0 and solve for x. And then our answer is going to be x equals any real numbers we end up with from step 2. So let's find the vertical asymptotes of any of the following functions. Let's start with number 2. I get f of x is equal to 2x minus 1 over x squared minus 1. The first thing we try to do is factor and reduce. I can't factor my numerator, so it's going to stay as 2x minus 1. But the denominator is the difference of squares, so it's going to factor as x plus 1 times x minus 1. Well, I look here, but there is absolutely nothing that I can reduce. So what I do is I just set the denominator, and I'm going to set the factor denominator equal to 0 and solve it for x. So if I solve the first one, I end up with x equals negative 1. And if I solve the second one, I end up with x equals positive 1. The final step is to figure out where you have vertical asymptotes at. We're going to have a vertical asymptote at x equal any real numbers you ended up with from step 2. Well, negative 1 is a real number. It's not imaginary. It does not have an I. And 1 is also a real number. Again, it's not imaginary. It doesn't have an I. So I have a vertical asymptote at x equals negative 1 and x equals positive 1. Now, if we wanted to show that, again, we could use the calculator to show this. So here in our y equals, we could put in the function. Our function is 2x minus 1 over x squared minus 1. I hit graph. Okay, so here's negative 1. This line that's drawn here on my calculator, this is an older version of this calculator, is actually the vertical asymptote. So here is the line x equal negative 1. Notice as we approach negative 1 from the left, we're going to negative infinity. As we approach negative 1 from the right, we're going to positive infinity. That's enough for us to see that x equal negative 1 would be a vertical asymptote of this graph. Same thing here for x equal 1. Here's x equal 1 on my graph. To the left of 1, I'm going to negative infinity. To the right of 1, I'm going to positive infinity. So x equal 1 is a vertical asymptote of my function. Right, let's do number 3. Step 1 is to factor and reduce. Well, I can't factor the numerator, and I can't factor the denominator, so I cannot do step 1. Step 2, set the denominator equal to 0 and solve for x. So I end up with 2x squared is equal to 0. Divide out my 2. X squared is equal to 0. Take the square root of both sides to solve for x, and you end up with x is equal to 0, because 0 is neither positive nor negative, so we do not write plus or minus. 0 is a real number, so our last and final step is just to say we have a vertical asymptote at x equals 0. So that is how we're going to find vertical asymptotes in this class. Again, if we wanted to, we could stick this in the graph just to prove to ourselves that we were right. Our numerator would be x minus 5, and our denominator would be 2x squared. And we hit enter. We hit graph, and then you notice here, right, here is x equals 0. To the left and to the right, we seem to be going to negative infinity. Therefore, x equals 0 is a vertical asymptote of this function.